Okay, this is about hiding variable light speed by mass manipulation in relativity. Einstein supposedly derived time dilation from his two postulates, but really it's just a bodge in the maths, and what should be variable light speed is hidden as time dilation. There are many such tricks in Einstein's relativity, just manipulating the maths to hide that it should really be Newtonian physics or make some mathematical mistake. And you see the derivation of Einstein's time dilation equation here. I will show this, and then I'll go through where the maths manipulation has happened to hide its variable light speed. So Einstein is starting from the principle of relativity and from the light speed constancy idea. And light speed is supposed to be in a vacuum, free of fields influencing it. So those are sort of the idealisations it's starting from. If we now start it up, here we go.
Hi, this presentation is about time dilation. I'll be trying to derive the time dilation equation. I'll also try to give you an example of how it might be applied.
First of all, I should say that it's by Mr. Tasingo. I'm not sure who he is supposed to be, but this is the sort of time dilation equation that is derived in most relativity textbooks. So it's fairly standard derivation.
So why is time dilation important? It's a concept that needs to be understood so that the derivation of relativistic mass increase can be comprehended. The concept of relativistic mass increase leads us to Einstein's special theory of relativity. So you basically can't get to Einstein's special theory of relativity unless you understand time dilation.
So, hold on a minute here. We're talking about relativistic mass increase, and in my video here I've dealt with it. This one here, it's relativist admits that mass does not increase with velocity, and when you actually look at the idea of mass increase with velocity, it leads to all sort of problems. And so I've got an example of this relativist who admitted that it is a mistake to say that mass increases with velocity, and he's still trying to hold on to special relativity, just he's not going with the mass increase thing. So it's led to all sorts of confusions just from this idea of mass increase, and they're trying to knock out the idea of mass increase with velocity to overcome the problems there. So we go back to the video. So what we're concentrating now is on the time dilation bit.
Now, to describe time dilation, I'm going to use an experiment of the mind. And in this particular experiment,
normally such things are called thought experiments.
I have a truck driver and a girl. The truck driver and the girl are stationary relative to each other. The truck driver is in a truck, and at the back of it there is a compartment. The walls of that compartment are transparent. Now, both the truck driver and the girl can see the goings-on inside that compartment, and anything they observe inside that compartment, any measurements they might make relative to what goes on inside that compartment, should concur. There's a light source at the roof of the compartment. The distance from the light source to the floor of the compartment, let that be known as h. A light pulse emanates from the light source and strikes the floor of the compartment. So as I mentioned previously, the girl and the driver are stationary relative to each other, and they're stationary relative to that light source. I'm expecting any measurements or observations they make to concur. Let the speed of light be known as c. Now, according to Einstein's second postulate, that's a constant, irrespective of the observer's frame of reference.
So we are going with that for the moment, and that's what Einstein's introducing. So we're working out the maths from that. I would sort of dispute that postulate has been properly applied, but we'll go with how it's been applied in this example.
The speed, as always, the speed of light, as always, is equal to distance divided by time. And the speed of light is equal to h, the distance covered, divided by t0. Now t0 is the time it takes for the light pulse to move from the light source to the floor of the compartment. And both the truck driver and the girl would agree that the light pulse covers that distance h in a length of time t0.
They're saying that they both agreed to time t0. Actually, I would dispute that, but we'll just go along with that for the time being, because this is what they do in normal relativity text. They suddenly say things like that.
Multiplying both sides by t0, you get h is equal to c times t0. So from now on, in any further calculations that I make, I'll be replacing that distance h with c times t0. Now, what would happen if we change something? We make the truck driver move forward. So the change is as follows. The truck driver moves horizontally relative to the girl. And he's moving horizontally with a constant velocity. So the truck moves horizontally a distance d relative to the girl. Now from the truck driver's perspective, he still thinks the pulse of light has travelled a distance h and took a length of time t0 to travel from light source to the floor of the compartment. But the girl's perspective is somewhat different. She sees the light pulse travelling a longer distance than before when the truck was stationary. Now the truck driver moves horizontally with the truck and with the light pulse. He thinks the light hasn't travelled horizontally relative to him. He only sees pure vertical motion by the light pulse. But the pulse has travelled horizontally relative to the girl. Now let the constant horizontal velocity of the truck relative to the girl be known as v. Now v is equal to d divided by t. Now that's actually the formula for average velocity, but I did mention before that the velocity of the truck is constant. Now the average velocity has the same magnitude as the velocity when the velocity is constant. Multiplying both sides by t, I get d is equal to v times t. And that's the distance that the girl sees the truck moving horizontally. And that black line represents that distance d. That distance d moved by the truck, but it's also the horizontal distance moved by the light source, moved by the light pulse, as seen by the girl. And let it be known as v times t. That green line represents the displacement, the magnitude of the displacement of the light pulse. It's the total distance covered as seen by the girl, the total distance covered by the light pulse. Now let that distance be known as c times t, the speed of light times t. and t is the time as measured by the girl, the time taken by the truck to move that distance d. That blue line is just that distance h. We worked it out before. It's c times t0. The truck driver believes the light pulse was in motion for a length of time t0. The girl believes the light pulse was in motion for a length of time t. I've got a right angle triangle there. I'll be applying Pythagoras' theorem. So what I've done in that equation is I've taken the length of the base and squared it, and I've added that to the square of the length of the height, and that is equal to the square of the length of the hypotenuse. I've minused v squared t squared from both sides. I've taken out t squared as a common factor. I've divided both sides there by c squared minus v squared. And now I'm going to change the way I express that fraction by multiplying it by 1. Now, it won't change the value of it, but look at the way I've expressed 1. That fraction, which is equal to 1, has been expressed as 1 on c squared over 1 on c squared. That won't change the value of anything, but it'll change the way I express things. And there's a bit of a change there, and I see c squared over c squared appearing, and wherever I do see c squared over c squared, I replace that with a 1. Now the expression looks like this. I'll square root both sides. I'll obtain the positive square root of the right-hand side. And what I have is the time dilation equation. I've derived it. And let's see whether I can apply it.
Right, that's the fairly standard derivation of the time dilation equation. So, my diagram there, you can see that, that's good. It's the same as what's on here. You've got the distance, there is CT, distance along there is VT, distance along there is CT0, and that's a right angle triangle. And then you've got the time dilation equation, T equals T0 divided by the square root of 1 minus V squared over C squared, and that's all there. That's that, the time dilation equation. Right, taking that equation, we can swap it over, just quickly swap it over. So it's T0 equals that, the square root of 1 minus V squared over C squared, and that's times T. So with that equation, we can then substitute it into there. So what we get is CT0. CT0 is equal to C times the square root of 1 minus V squared over C squared times T. So we can just drop the CT0, and so what we get is just that. You've got CT along there, VT along there, C times the square root of 1 minus V squared over C squared, and that's times T. What we can do is we can divide through by T, divide through by T there, by there, divide by T, divide by T there, so we're just cancelling out the T's, and when we do that we get that. Got that. So that's still not very good. We've got that back triangle. We've got C along there.
Now, some beta particles move very quickly and they're ejected from radioactive.
We've got C along there, V along there, and C times the square root of 1 minus v squared over c squared there. So what we've got along that direction, we haven't got the speed c. We can try to pull it up again. There. There's that close, so it's that. So instead of having variable light speed, having a variable light speed along there, they're putting in this t0. They're hiding variable light speed by use of t0. So this little lady here, when she's looking at this triangle here, what she's really seeing is the speed along there is c, speed along there is v, and the speed up there is c times the square root of 1 minus v squared over c squared. It's not that. No nonsense about it being t0. It's t along there, t along there, t along there, not t0. So they're trying to pretend that there's time dilation instead of what it really is from Newtonian physics as that c along there, v along there, and c times the square root of 1 minus v squared over c squared. That's the little trick they try to do. They can't even do their maths properly. So that's where they are. That's where they are. They're trying to hide variable light speed as time dilation in that particular thing. It's Newtonian physics. It's just basically Newtonian physics, and they've bodged it. They can't even see that they're bodging it. There is no time dilation going by Newtonian physics. What you have is a variable light speed. Speed c along there and a different speed along there. That speed is not going to be the same as that speed along there. And they're trying to pretend it is. C there, and it's not c along that way. So they've just bodged it. If we go by Einstein, he is introducing the idea of assuming light speed is constant or something like that, and by doing that he's just messing the maths up. He's just messing the maths up by trying to put in time dilation. So he's hiding variable light speed by introducing time dilation. It's just nonsense. In Newtonian physics you don't have clocks all going at different rates. You have the clocks going at the same rate. And you also, when they get to this, it's supposed to be behind understanding relativistic mass increase. And as I pointed out earlier from that video, they end up with lots of problems with that. So it's just a continuation of making problems there. So I've got another video. Other people have looked at this for Einstein's relativity, and it just does not really make any sense. If we go cuckoo process there, that's it. When people try to look at Einstein, this is a sample here of G. Bernstein Brown. When you look at Einstein and you know a bit of maths and you're saying what's going on here, what Einstein does is just goes cuckoo on you. That's basically what's going on. Instead of having that with variable light speed, he's trying to pretend that there is time dilation, and he makes that mistake there. And he makes more and more mistakes as he goes on. He should really be dealing with Newtonian physics. So why does he make all those mistakes and then pretend he's not got Newtonian physics anymore? It's just a mess. everything is just a mess. So what we have, when you look at Einstein, you can say to yourself, he's talking nonsense. It's just nonsense. All of it is just nonsense, built one on top of the other. Looking at Einstein and saying he's talking nonsense is a valid conclusion. Thank you.